Hello all, welcome back to AK Apt Logics. Today in this class we are going to discuss about NAND gate, design of NAND gate using the switch level model. This is the most important model that no one discuss in the uh, online. So I am going to discuss about the NAND gate designing in switch level model. Okay. So without any delay, let's start the video. For example, in the previous class we have discussed about the behavioral model of NAND gate, and also we have discussed about the data flow and then uh, gate level modeling, right? So today in this class we are going to discuss about the switch level modeling. Okay, to know this particular lecture you need to must watch the my previous lecture that I have discussed about the switch level model in the NOT gate. Okay, how to write the switch level code for the NOT gate I have discussed in the NOT gate video. So you just watch that video, then only you can able to understand what I'm going to tell you now. Okay, so in every lecture I'm going to say you, right, our TB is always same for any style, any levels of for any level of abstraction. Our TB is always same. Only when you are going to change the module name over here. For example, if I am going to change the module name over here, that is I have added the switch, then you need to add, and then you need to change the instance name in the TB. Here you need to add switch, that's it. Other than that, there is no need of changing the TB. Okay, if you are going to change the module name of design code in the design code, then you need to change the instance name of that particular module in TB. That's it. Otherwise there should be no any changes in TB. Okay, and in Verilog we are going to mostly focus on the design code. We are not going to focus on the TB. In system Verilog we are going to focus mostly on the TB. Okay, we are not going to focus on the design code. Okay, we are also focus on the design code, but mostly we are going to focus on TB in the system Verilog. In Verilog we are going to mostly focus on the design code. Okay, without any delay, let's start the video. For example, what are the changes that we are needed to do in our behavior model code to get the switch level model is we need to remove this particular matter always block. Okay, everything will be same, module NAND gate input output, and then you need to remove this reg. Okay, only in behavior model you are going to mention outputs as reg. Otherwise, in all other styles you are going to take inputs and outputs as wires, but you are not going to mention wire like this. Why? Because by default input and outputs are considered as wire data type. Okay, only in behavioral model you should make the outputs as reg, so that you are going to mention them as reg. Okay, in switch level model also we are going to take inputs and outputs as wires. Okay, only the output in behavioral model is treated as reg. Other than that, in all levels of abstraction the input and outputs are treated as wires. Okay, so how to write this switch level code? Okay, for example, if you are going to take the gate level model, we are going to, for example, if we are going to take the gate level model, then we should know the logical diagram of that particular circuit. For example, if you are going to write the code in data flow model, then you should know the boolean expression for that logic, right? For example, if you are going to write the code in behavioral model, then you should know the truth table of that particular design. But coming to switch level model, you should know lower level details. Okay, you should know very lower level details. Those are transistors. Okay, so mostly we are going to use the CMOS technology, which is having low power. Okay, mostly we are going to use the CMOS technology. Why? Because it is having the low power, and also in our academics mostly we are going to deal with the CMOS technology. There are so many technologies like BiCMOS, fast transistor logic, TTL logic, and then ECL logic. Okay, these are the logics. Okay, in the NOT gate video also I have discussed about the CMOS technology. Okay, to write the code for the NAND gate, first you should know how does this particular NAND gate looks like in a CMOS technology, CMOS diagram. Okay, you should know that. Okay, you should know how does this NAND gate looks in the CMOS. Okay, for that only I'm going to ask you guys to watch the previous video of my NOT gate, which I have discussed um, in the switch level model, right? So if you are going comfortable with CMOS, and you know how to draw the CMOS circuit for the NAND gate, then no problem. Okay, if you are not aware about CMOS technology, then please watch that particular video, then only return to this particular video you can able to understand what I am going to tell you. Okay, so for example, we are going to take the CMOS technology to write the code in switch level model. What is meant by CMOS? CMOS is nothing but the complementary metal oxide semiconductor. Complementary metal oxide semiconductor. CMOS involves both PMOS and NMOS. Both PMOS and NMOS. Okay, CMOS is nothing but the combination of both PMOS and then NMOS. Okay, for any CMOS circuit, okay, for any CMOS circuit, there are two types of regions or two types of circuitry in our code. One is the pull-up network. Okay, one is the pull-up network. Okay, pull up. Sorry, spare my handwriting. Okay, pull-up network. Let me show the network like this. Okay, pull-up network, and another is the pull-down network. Okay, I am going to cover the basics. Okay, another is the pull down network. Pull down network. Okay, pull down network. So we are going to give the high voltage to pull up network. Okay, we are going to give the high voltage, that is VDD, to the pull up network source terminal. Okay, I am going to discuss. Okay, we are going to give the high voltage VDD to the pull up network, and we are going to give the low voltage to the pull down network, that is VSS. Okay, now we are going to join both of the pull up and pull down network drain terminals. Okay, we are going to join the pull up and pull down drain terminals, and we are going to take the output from in between them. Okay, we are going to take the output from in between them, and where we are going to apply the input, we are going to apply input both the pull up and pull down networks. Okay, we are going to apply input to both the pull down and pull up networks. Okay, okay, now what is pull up network and what is pull down network means? Pull up network is the network in which it going to consist of PMOS transistors. Okay, the pull up network is completely made up of PMOS transistors, using PMOS transistors, whereas pull down network is completely made using the NMOS transistors. Okay, and you need to remember a point, that is, in CMOS technology, the PMOSs in pull up network is always equal to the NMOSs in pull down network. Okay, you need to remember that point. Okay, so how does this PMOS looks like? Let me discuss with you. The PMOS seems like this. Okay, there is a bubble at the gate terminal, and there are two other terminals, those are source and drain. Okay, this is the gate terminal, and this is the, for example, drain terminal, and then this is the source terminal. Okay, how does this NMOS looks like means, there is no bubble at the gate terminal. Okay, okay, there is no bubble at the gate terminal. So if you are going to take the NMOS, then it is also having gate and then drain and then source. Okay, where we are going to apply the input. Okay, we are going to apply the input. Okay, we are going to apply the input at gate terminal. Okay, for both the NMOS and PMOS, we are going to apply the input at gate terminal, and we are going to apply the source voltage, those are VDD. For which we are going to apply VDD, we are going to apply VDD to the pull up network. It means we are indirectly applying VDD to the PMOS transistor. VDD we are going to apply to PMOS transistor source terminal. Okay, we are going to apply VDD at PMOS transistor source terminal, and VSS at NMOS transistor source terminal. Okay, we are going to apply VSS to the pull down network. Pull down network means the network which is made up of NMOS transistors, and we are going to apply that particular VSS to the source terminal of the NMOS. So from where we are going to take the terminal output, we are going to join both of the drains, and then we are going to take the output from that particular common point to the both pull up and pull down network. Okay, this is the basic information that you guys need to know about the CMOS technology. And the basic gate in the fundamental or the basic gate in the CMOS technology is NOT gate, not the buffer. Okay, the fundamental gate in the CMOS technology is NOT gate or inverter. It is also called as inverter. So that only I have discussed you about the NOT gate initially, and then NAND gate. Okay, okay, inverter, NOT gate or inverter. We are going to consider as fundamental gate in the CMOS technology. Why? Because in the previous lecture you have seen it, right? We are going to get the complemented output. That's why only we are going to tell it as complementary metal oxide semiconductor. We are going to get the complement output. Okay. So now we would like to design the circuit of the NAND gate. Okay. I have discussed how to design the circuit of the NOT gate in the previous class. We just watched that particular video. So now let us see how this particular NAND gate is made. For that you need to know the NAND gate equation. What is that NAND gate equation is? For example, output, let us consider it as Y is equal to A dot B bar, right? So you need to remember a point, that is, for any logic which is consisting of whole bar, okay, for any logic which is consisting of whole bar, then that particular circuit can be designed easily in the CMOS technology. We can design easily in the CMOS technology. This circuit we can design easily in the CMOS technology. Why? Because we are going to get this particular complement operation at the end of the CMOS technology without adding any circuitry, so that it is very easy to get the output of NAND gate in the CMOS technology. You shouldn't care about the whole bar. Okay, you shouldn't care about the whole bar. You need to implement just the internal logic below the whole bar. Okay, so when you are going to implement the internal logic which is below the whole bar, then automatically you are going to get the output of this particular NAND gate. Why? Because the CMOS is in CMOS we are going to get the complemented output, right, at the output. Okay, so how to design this particular circuit? You need to remember two more points. That is, first point is you need to check number of inputs. Okay, number of inputs to our design. You need to check number of inputs to our design. Here in this case, how many inputs we are going to have? We are going to have two inputs, right? Here in this case we are having two inputs. Those are A comma B. A comma B are the two inputs in this case, right? So your number of PMOS and NMOS transistors will be equal to the number of inputs. Okay, this is the point you need to remember. Number of in PMOS, number of PMOS, number of PMOS transistors. Okay, number of PMOS transistors in pull-up network, right? I already told you why pull-up network is called as pull-up and why pull-down is called as pull-down in the NOT gate discussion. You just watch that particular video. Okay, pull-up network, number of PMOS in pull-up network will be equal to number of, okay, I'm just using it, number of NMOS, right? This thing I have already told you. Okay, in pull down network, right? In pull down network, in, for example, I'm going to bring that particular text down. Pull down network will be equal to number of inputs, will be equal to number of inputs, will be equal to number of number of inputs that we are going to have, inputs that we are going to have in our circuit. Here in this case we are going to have two inputs, right? Those are A and then B. Okay, it means in pull-up network we are going to have how many pull-up PMOS transistors? 2. And in pull-down network how many NMOS transistors we are going to have? 2. Okay, this is the point you need to understand. This is the first point which I told you to discuss. And the second point you need to remember is you need to see the operation in between the variables under the whole bar. You need to see the operation in between the uh, variables. We need to see the operation between the variables under the whole bar. Either it will contain or operation, or it is going to contain and operation. Okay, either it is going to contain or operation, or it is going to contain and operation. Or operation, for example, let us consider it as some operation. Okay, we shouldn't call it as sum, but I am going to tell you in a simplified way. And dot operation, let us consider it as product. Okay, let us consider it as product. So now what we need to see is we need to see the type of operation. First step what we need to do is, first step is this: you need to identify number of inputs, and then you need to identify number of PMOS and number of NMOS transistors that you are going to required by you in the pull up and pull down networks. Next step what you need to do is you need to observe the operation between variables under the under the bar, under the complement bar. Okay, whole bar, right? In this in our case it is product, right? In our case it is product. There is under operation between A and B. If it is product, if it is product, then what you need to do is, if it is product, you need to do two steps. One is you need to connect the PMOSs, the PMOS transistors in parallel. Okay, PMOS transistors in parallel at in the pull-up network. You need to connect PMOS transistors as parallel. Okay, in pull-up network, and you need to connect NMOS transistors in pull-down network as series. Okay, series. So if you are going to have this summation operation, then it will be reverse. It will be reverse in the sense PMOS transistor in the pull-up network will be connected as series, and NMOS transistors in the pull-down network are connected as a parallel. Okay, now you got the basics of how to design the circuit. Okay, now how to connect the parallel configuration of two PMOS transistors. Those are having the total 3 terminals, right? How to connect them as parallel means you just short the two drains of the two PMOSs. We are going to short the two drains of the two PMOSs like this. See, for example, this is one PMOS, this is one PMOS. Okay, this is another PMOS. Okay, this is one PMOS, this is one PMOS. Okay, which is having gate. Okay, this is having gate, and this is also having gate. This is having drain, and this is having drain. This is having source, this is also having source. You just connect two drains to each other, and you just connect two source to each other. Then what about the gate? I already told you, right? We are going to apply the input at the gate terminal. What are the inputs? In this case we are having the inputs as A and B. You are going to apply one input A to the one gate terminal of the PMOS. For other terminal of the gate, for other terminal gate terminal of the second PMOS, you are going to apply input B. Okay, This is how we are going to make the parallel connection. Okay, series, how we are going to make the series connection in the sense, for example, uh, this is the PMOS. Okay, this is one PMOS and this is another PMOS. Okay, you are going to connect, you are going to connect drain and source. Okay, you are going to connect drain and source, you are going to connect drain and source. This is source, for example, this is drain, this is source, and then this is drain. Okay, you are going to connect source and drain. Okay, source terminal of one NMOS to drain terminal of another NMOS you are going to connect, then it is going to be have the uh, series connection. And what about the gate terminal? The gate, for the gate terminal you are going to give both the inputs. For one gate terminal you are going to give input A, and another terminal we are going to give input B. So this is how we are going to perform. Okay, let me draw the NAND gate circuit for you. Okay, let me take the black color. Okay, so let us draw the pull up network. Okay, in pull up network what we are going to have, as per our discussion, PMOS, right? Let me draw two PMOS transistors. Okay, let me draw two PMOS transistors. This is one PMOS. Let me draw another PMOS transistor like this, in this manner. Okay, this is also PMOS and this is also PMOS. Both are PMOS transistors. Let me indicate the terminals. Okay, what are the terminals? With blue color. Okay, this is the gate terminal, right? This is the gate terminal, and this will be the source terminal, and this will be the source terminal, and this will be the drain terminal, and this will be the drain terminal. Okay, this is the gate one, this is the source one, this is the source drain one, and drain two, and then source two, and then gate two, right? What we are going to do, we are going to short. In this case what we need to do, we should connect them as parallel. Why? Because there is a product operation in between A and B, right? So that we are going to connect them as parallel. So we are going to join two source terminals and two drain terminals. Okay, and what we are going to do, we are going to apply first input to first gate, that is first input, that is A, to gate terminal of first PMOS, and then second input to the gate terminal of second PMOS. Okay, like this we have done. Now for source terminals what we need to give, this is the pull up network, right? For the source terminal we are going to give the VDD, power supply, right? So for source terminal you are going to give the VDD. Okay, you are going to give the VDD, which is the high power supply. Okay, now just leave the drain terminal like this. Okay, I am going to discuss this. Now let us draw the pull down network. In pull down network what we are going to have, we are going to have two NMOS transistors. Why? Because we are having two inputs, right? So that we are going to have two NMOS transistors. Let me draw two NMOS transistors. Okay, this is first NMOS and this is second NMOS. Let me mention the gate and source terminals. Okay, this is gate 3, this is gate 4, and this is source 4. Okay, this is drain 4, and this is source 3, and this is drain 3. Now what we are going to do, we need to connect both the NMOS transistors in series. Why? Because there is a product operation in between our variables, so that we are going to connect both the NMOSs as in series. To connect them, how should we connect the terminals? We need to connect source terminal of one NMOS to drain terminal of another NMOS. Like this we should connect, right? So, and to for the two gates, for the two gate terminals we are going to give both the inputs, that is input A and then input B, right? Input B, right? And then for the source and the for source terminal for the second, for the source terminal for the second NMOS transistor we are going to give the low supply, that is VSS. Okay, this is the pull down network, right? This is the pull down network. This is the pull down network, right? Okay, now we are going to extend this particular drain terminal above. From where we are going to take the output? From where we are going to take the output? If we are going to see from the common connection between the pull up and pull down network. Okay, to get the common connection you need to join this particular two and then you need to take the output from this point. So our NAND gate is ready. Okay, so let us see whether it is performing the NAND operation or not. So let us apply input combinations. We are having total two inputs, then we are going to have total four input combinations. Those are 0 0 and 0 1 and 1 0 and then 1 1. 0 means 0 volts, 1 means 5 volts. Okay, let us first apply 0 0. Okay, we are going to apply A equal to 0 and B equal to 0. Okay, PMOS will be turned on when we are going to apply 0 to its gate terminal. It means it is going to turn on. It is going to turn on. Okay, both the PMOS transistors in the pull up network are going to turn on. Both the like this, both the PMOS transistors in the pull up are turn on and going to short like this, and both the NMOS transistors in the pull down network are going to turn off. Why? Because when you are going to apply the 0 to the gate terminal of the NMOS transistor, it is going to turn off. Okay, like this, it is going to turn off. So then what happens is we are going to have the clear path from VDD to the output. We are going to get the VDD to the output. It means we are going to get the high voltage, right? Then output will be 1. Okay, then we are going to take output will be 1. This is A, this is B. Okay, output will be 1. Okay, let me discuss you with you another case. For suppose if we are going to apply, let me mention these values A and then B and then B by, we have seen the first condition, right? We have got the output as 1, that is VDD, right? So for the case we are going to apply A is equal to 0 and B is equal to 1. Okay, and then again A is equal to 0, B is equal to 1 to the pull up and pull down network. Then this particular first transistor of PMOS is going to turn on and it is going to have the short path like this, and the second PMOS transistor is going to turn off. Why? Because we have applied the 1, but PMOS will turn on when you are going to apply the 0, right? So it is going to turn off, where in this case the first or the third transistor, that is the first NMOS transistors is going to turn off. Why? Because we have applied 0 to its gate terminal, it is going to turn off. If you are going to see the G4, that is second NMOS transistor, we have applied 1 to it, it is going to have a clear path, that is on, the transistor will get on. Okay, now if you are going to see the path to the output, we are having path like this, we are having path like this, right? We don't have path like this from VSS to the output. Why? Because the third transistor, that is the first NMOS transistor is got off, right? So that you don't have path from VSS to Y, that is output. You are having path from VDD to the Y, so that again you are going to get output as 1. Why? Because we are going to have a clear path from VDD to Y, right? VDD is a high voltage, so that we are going to get high voltage, so again we are going to get the 1. Okay, Now you do the case for the third case 1 0. I am going to discuss with you guys with the 1 1 case, last case. Okay, 1. This is for you. Okay, this is for you. Just verify it whether it is going to get or not. 1. This is for you, right? Yeah. Let me apply 1 1. Okay, I am going to apply A equal to 1, A equal to 1, and then B is equal to 1. It means we are going to give the high voltage. For 1, the both the NMOS PMOS transistors in the pull-up network are going to turn off. Okay, for 1, both the NMOS transistors in the pull-down network are going to turn on. It means these are going to have a short circuit, and these are going to have a open circuit. If we are going to see the path to output Y, there is no path from VDD to Y. There is a path from VSS to Y, right? There is no path. There is no path like this. Okay, there is no path like this. There is also no path like this. It means there is no path from VDD to Y. There is a path from VSS to Y. Why? Because both the NMOS transistors are in series, and both the NMOS transistors are got on. So we are going to get output as VSS. In output we are going to get the VSS. VSS is the low voltage, so that we can able to represent it with the 0. So it means we got 0 when we have applied the both the inputs as 1 1. So it means we got the output as 0, right? Okay, for the third case you are going to get 1. Okay, you just verify it. I haven't discussed about it. Okay, if you are going to see the operation, if you are going to clearly observe this particular table, then this is the table for the NAND gate, right? We got the NAND gate operation. Okay, we just implemented the logic under the, we never cared about the whole complement. We just implemented the logic under the whole complement. Okay, even though we have just focused on the internal logic uh, in the whole complement, we got the complemented operation, right? So that this particular CMOS is called as complementary. That's why only at the end, at the output you are going to get the complemented operation. Okay, so this is all about the uh, NAND gate. Okay, I hope you got how did I done it. So let me show you the code, how to write the code for our NAND gate in switch level model. So we just know what we have done is we got the circuit of this particular NAND gate in switch level model, that too using the CMOS technology. There are so many several technologies as well. Okay, those things mostly most of the people don't discuss about those things. So I'm also not going to discuss about those things. I am going to focus on the CMOS technology. Mostly most of the people don't even discuss about the switch level model. Okay, but I have discussed because it is important to know. Okay, so let me write the code for the NAND gate CMOS technology. Let us write the code. Okay, I am going to change it to the switch level model. Okay, I am using the split screen. Okay, switch level model. So we have taken the inputs and outputs. The port list will be same, and the end mod is also same. So you need to, here we are going to use the primitives. Those are PMOS primitive and NMOS primitive, like this we are going to use. So let us consider this particular PMOS as P1 and this PMOS as P2. Okay, and then this PMOS as P3. Okay, let us consider it as N1. It is going to be N1, right? Let us consider this particular transistor instance as N2. Now we are going to use 4 primitives. Okay, 4 instances. Those for one is for P1 and one is for P2, and then one is for N1 and then one is for N2. Before that, what you need to do is you need to get this particular supplies, VDD and then VSS. We are going to supply 1 or the high voltage to the VDD, and we are going to supply 0 or the low voltage to the VSS. For that we are going to have a keyword, that is supply 1 VDD. Okay, and then supply 0 VSS. Okay, we have given the supplies. Now next what we need to do is we need to create 4 instances of the 4 transistors. First let us create the PMOS transistor. Low. So for example, PMOS is the primitive name and it is the P1, right? The transistor we have considered it as P1, right? P1. And in the braces you need to give total 3 parameters. Why? Because for the PMOS transistors you are going to have the 3 terminals, so that you need to include 3 parameters. Okay, the first parameter must be the output. The first parameter must be the output. It means the first parameter must be the drain terminal. Okay, the first parameter must be the drain terminal. Second parameter must be the source terminal, and the last parameter that you need to give is gate terminal. Okay, so like this you need to give. Let me comment this. First of all, let me comment this. Okay, and give you PMOS P1. Okay, what is connected to the drain terminal? For drain terminal we have connected Y, right? See, for this particular D1 we have connected Y, so that you need to mention Y as first parameter. What is connected to the source terminal? Okay, what is connected to the source terminal? That is VDD, right? So that you need to give VDD as second parameter. And for the third parameter what you need to give is what is connected to the gate terminal. For gate terminal we have connected the input A, so that you need to mention A over here. Okay, and close the parenthesis and then put the semicolon. Okay, this is how we are going to uh, create. We have created the instance of P1. Okay, now we are going to copy this particular line. Okay, this is comment. Okay, don't worry, this is the comment, single line comment. Okay, even if you are going to remove this, no problem. Okay, let me copy this particular line and then create the P2 instance. Okay, these are the primitives, built-in primitives, and the instance name is P2, right? For P2. And for drain terminal of P2 what we have connected? We have connected Y. Again we have connected Y, right? So I am leaving the Y as this. For source terminal of P2 what we have connected? We have connected VDD, right? For source terminal of P2 we have connected VDD, so I am going to leave it as well. For gate terminal of P2 we have connected B, so that replace A with B. Okay, I hope you understand how I am going to code in switch level model. I am going to use this particular circuit. Okay, so that only for our last half an hour discussion we have discussed with the circuit is the most important part in this switch level model. We need to know lower level details about the transistors. Okay, this is most important. Okay, now let us take NMOS. NMOS is a primitive, and let us take N1. Let us write the instance for the N1. Now similarly it is also same. First you need to mention what is connected to the drain terminal. If you are going to see the drain terminal of N1, if you are going to see the drain terminal of N1, it is connected with output Y, right? So I am going to give Y. Okay, Y, comma. If you are going to see the source terminal of N1, then it is connected to the drain terminal of D4, right? Then it is connected to the drain terminal of N2, right? So that you just leave it. Okay, you just leave it. I am going to tell you what we need to do. Okay, and then if you are going to see what is the value that is connected to the gate terminal of N2 N1, that is A, right? We have connected A to the gate terminal of N1, so that you need to give A over here and then close the parenthesis and then semicolon. Now let us take the another NMOS instance and create and write for the N2. And what is connected N2? For drain terminal of NMOS, what is connected? For drain terminal of N2, what is connected? We have connected it with the source terminal of N1, right? So you just remove it. We haven't connected the Y, right? So that I am going to remove it. You just leave it. I am going to tell you what we need to do. Okay. Next, For source terminal of N2, what we have connected? We have connected the VSS, right? So that you just mention VSS. For gate terminal of N2, what we have connected? We have connected B, right? So you just replace the A with B in code. Okay, you need to observe, okay, what is connected, and then you need to give it. Okay, now we are left with one value. Okay, that is this region. Okay, this region we are going to left with this particular region. Let me show you highlight with another color, or let me zoom it. So now we are left with this particular region. Okay, source terminal of N1 and drain terminal of N2 are connected, but what value you need to give in that place? In that place, what value you need to give? You need to mention. See, if you are going to see, source terminal of N1 is left with empty, and also drain terminal of N2 is left with empty. But you know, source terminal of N1 and drain terminal of N2 are connecting to each other. It means both are the same value, right? They are connecting to the each other, but you don't know what value you need to mention. Okay, then you are going to use the concept of wire, so that we are going to use the internal wire. Why? We are going to mention it as W. Okay, it means it is nothing. We are going to assume this particular wire as W. Okay, now source terminal of N1 is connected with W, as well as drain terminal of N2 is connected with W, so that we are going to mention W and then W. That's it. Okay, I hope you understood when to use the internal wire. Okay, in this case we need to use internal wire, and why we have used, I explained you very clearly. Okay, so our uh, code is ready. Switch level model code is ready. Okay, you shouldn't need to change TB single line. Okay, you shouldn't change the TB at all. You shouldn't need not to be changed the TB at all. Okay, and the point you need to remember is why we are going to use the YW. Okay, you need to use why not reg. Why not reg? In the sense, we are not going to use any flip flop, right? We are not going to use any flip flop in this place, right? We are not going to use any flip flop in this place. We have used the wire, so that we are going to use the wire data type, which is used to continuously driven the output, right? It is not going to store any value. It is going to just pass the value, right? So now we have finished with our switch level coding for the NAND gate. Okay, we shouldn't need to change our TB. If we are going to change the name design code module name, then you need to change the instance of that particular module name in the TB. That's it. If you are not going to change that particular design name as well in the design code, then you know you shouldn't touch the TB at all. Okay, why? Because we are not going to discuss more about TB in very long. We are going to focus mostly on the design code. Okay, we will focus mostly on the TB in the system Verilog. So let me save the code. Before saving the code, let me select the tools. Let me select the first tool and then save the code. Okay, after saving the code, let me run the code. If you want my TB explanation, you just watch the NAND gate using this gate level model. In that, I have explained you my TB. Okay, how did I wrote it? I told you. Okay, you just watch that particular video. Okay, then you can able to understand how that particular gate is used. So you can see the output in the console. Whenever the both the inputs are 1, we are going to get the output as 0, right? For all other cases, we are going to get the output as 1. So this is the operation of the NAND gate, right? So we have achieved the NAND gate operation using switch level model in Verilog. So let us see the waveform as well. For that, what you guys need to do is you just select the open EPWave after run, and then save the code and then rerun the code. Okay. So the waveform window will be popped up to you. So whenever the inputs are 0 0, see, whenever the inputs are 0 0, you are going to get the output as 1, and whenever the inputs are 0 1, you are going to get the output as 1, and whenever the input is 1 0, you are going to get the output as 1, and whenever the input is 1 1, okay, whenever the input is 1 1, you are going to get the output as 0. Okay, you just analyze the particular timing things. Okay, I have told you how to analyze the timing details, so you just watch the previous video, then you can able to understand how it does this particular time equal to 60. I have explained you what is meant by time equal to 60, what is meant by time equal to 30. In this video, I am not going to explain why, because I just showed you the output. Why? Because already it is uh, duration of 45 minutes. If I am going to explain it, it is going to take up to 50 to 55 minutes. So that I am going to pause the video here itself. So I hope you got and you have understood how to write the code for this NAND gate in the switch level model. You just need this circuit, switch level circuit, using any logic. I have used here CMOS logic, so that I have written code. Okay, thank you guys, have a nice day.